Okay, let's start. Good morning, everybody. Welcome back to the Escape Summer School, 5th day. And this morning, we welcome Axel Donat, who is working in gamma ray astronomy and maintainer of the GammaPi package, who is using a lot Scipy and AstroPy. And so this morning, the first lecture is on Scipy.
Thanks a lot, Thomas, for the introduction. Yes, so the sessions will be twofold this morning. So in the first part, we're going to take a look at the Scipy package, and then we're going to do a coffee break. And then after the coffee break, we're going to take a deeper look into the AstroPy package. Just as a quick reminder, just to get the latest material on the course, just go to the repository and just type git pull, and then you will get the latest version of all the teaching materials. Then you can just change to the Scipy folder, and then just start your Jupyter notebook either by typing Jupyter notebook or using Jupyter Lab, whatever you have used in the past. Okay. This I've done. Okay, let's take a look at the Scipy tutorial. So on Wednesday, we've already heard about the NumPy package and the pandas package, and those basically provide data structures. Now, on top of that, we often want to do a certain kind of analysis. We want to run a certain algorithm on the data. And there, Scipy is really like a good solution to provide like the basic building blocks for analysis of data and algorithms of any kind. The structure of the course and the notebook is roughly that I would just recommend that you just execute the code cells along on your local machine. There are a few exercises in between. Unfortunately, the time is very limited. So my recommendation would be that you just take a look at the exercises after, but there are sample solutions in the solution folder. And then if you have questions to the exercises and the solutions or anything, just use the Slack channel, and we're going to be online a lot after the course to answer those questions and to help. Okay, so this is the logo of Scipy, and here's a quick overview on the functionality that Scipy provides. Scipy is structured into sub-packages with a different focus. So for example, there's Scipy Special to provide access to special functions. There's integration and ordinary differential equation solving. There's optimization, interpolation, Fourier transforms or fast Fourier transforms, signal processing of any kind, linear algebra, also eigenvalue problems and sparse eigenvalue problems and handling of sparse matrices. There's statistics, also multidimensional image processing, and also some functionality for I/O and serialization of special kind of data. We're going to take a look at these sub-packages step by step and one by one. In general, so this is also the entry point to the documentation of Scipy, so you can always just click there, and then you will be redirected to the corresponding page of Scipy, of the Scipy documentation. And this is always like a good resource of information, of course. Always check the documentation of the package. Okay, so let's just dive in and just start with a quick setup. Just a few usual imports. I think those you've seen multiple times, just to provide the inline or to provide the inline plotting for matplotlib. And then, of course, we're going to use NumPy. This you've already know. And then we're going to do a little bit of 3D plotting. This is what this axis 3D object is for. And then we also do a bit of random number generation. And there it's always a good idea to rely on the new API of NumPy to define a global non-mutable state for your random number generation. Okay, let's start with the linear algebra. So the linear algebra modules contains a lot of matrix-related functions, including like solving of linear equations, eigenvalue solvers, matrix functions, for example, matrix exponentiation or decomposition, such as singular value decomposition or lower upper decomposition or Cholesky, etc. Again, just a link to the detailed documentation. So typically, linear equation systems can be just written in the form of the matrix vector multiplications, where you have just a matrix A times a vector x, and then this equals the vector b, just as a quick reminder. And this we can just directly generate here in the notebook. So we're using NumPy to define a matrix of the size 10 by 10, and then we're just adding random number entries to this, that we are having at least some data to work with. And the vector b is just created with NumPy arrange. Here's a little helper function. For example, if you want to visualize a matrix, then you can rely on plt.mathshow, and then you will see a nice visualization of the matrix inline in the screen. So that's what our matrix looks like. And then we can import from Scipy the linalg subpackage, and this provides a method that is called solve. And this will then solve the linear equation system defined by the matrix E and the vector B. So if we just run this, then we get our result vector. I mean, we've used random numbers here, so it's hard to verify whether this is actually correct. But one way would be just to compare it against the inverse operation. So for this, we can just rely on the dot product of NumPy. So we can multiply the matrix A with a vector X, and then we can subtract our solution vector, and this should be reasonably close to 0. And as you can see, if you print out the vector here, this is the case. One could actually, I think we've seen this before, one could actually use something like NumPy all close. To 0, and then you will also see, in this case, it's false, but you can specify, for example, a tolerance that this is actually fulfilled. Still not, well, maybe it's still not true. Sorry, I missed the minus b here. And now this is actually true. Just another example, the same works also for in the case where A, X, and B are all matrices. So again, we just create a few random matrices. This time we just rely on filling the matrices with uniform distribution, and the size of the matrices is just 5 by 5. Let's just visualize those. So here's matrix A and here's matrix B. Again, we just rely on this mathshow command. We can switch off the grid because it would be disturbing in this case. And I'm just setting the title here to illustrate the matrices. And then we can actually use the same function and the same API to solve for the exact same problem that we've defined. And then again, we can just verify here that the norm of the dot product of the both matrices minus the result matrix here is actually reasonably close to 0. Okay, another very common problem in linear algebra is eigenvalues and eigenvectors. Just a quick reminder, so the eigenvalue and eigenvector problem is formulated like this. So you have a matrix A here, which is multiplied with the eigenvector, and what you get as a result here is the eigenvalue times the eigenvector. And Scipy provides a little function to help you with that and to solve this problem. And this is called eigvals. So it's the shortcut that they use here. And this will actually do both. So it will calculate the eigenvalues and eigenvectors at the same time. And in this case, both return complex numbers. It depends a bit on the definition of your matrix. So again, we just create a random matrix of the size 4 by 4, and then we can run linalg.eigenvalues on this matrix, and then you can see that you'll get back the result object here. There is so this will just return an array of eigenvalues. So this you can verify. So the length here is 4. So there are 4 associated eigenvalues. And then if you want to have both, like the eigenvalues and the vectors, then you can just rely on linalg.eag, and this is shown here. This then actually returns both, where values now is the array of eigenvalues for again, and then if you check, for example, the vectors shape, then you have the associated vectors stored in the matrix, where each vector corresponds then to the corresponding entry of the eigenvalue. I hope this makes sense. Okay, here's just a little exercise. That's called simple linear algebra. You can basically repeat this little exercise just yourself and try it yourself in the notebook. But I would recommend now just to follow along, and then go to the exercise later as a kind of homework. There are sample solutions I can just quickly show. Those you can load into the notebook just with this %load command, and then you can take a look at the sample solution and compare, for example, whether you found the right one. Okay, let's continue with the next subpackage of Scipy. So there's one package that provides special access to very special functions. So really, like a large number of mathematical problems require special functions or are solutions of certain differential equations. And these are provided in the special subpackage. For example, there are defined the area function, elliptic functions for integrals, Bessel functions, gamma functions, etc. Again, you can just go to the documentation here, and then you will see like what's available. Bessel functions, Hankel functions of certain kinds, integrals of Bessel functions, derivatives, spherical Bessel functions. So you get a nice overview of what's available there actually in the documentation. Let's just start to use it and give you a quick overview, for example, on the built-in polynomials. And there's just a little example of visualizing those for certain orders. So we're going to take a look at the Chebyshev, Laguerre, Legendre, and Chebyshev of second kind polynomials. And this is just a little overview plot. So I'm creating the multiple axes here. I think we've seen this before already. And then I'm evaluating the polynomials in a range from -2 to 2 with 200 bins. And then I'm just doing this loop over the functions already. I'm not sure whether you've seen this zip command before. This basically does the joining of two lists or two iterable objects. So here functions is the dictionary, this is iterable. And then this axis object here is also iterable in the same way. And then zip will join both and return a tuple that you can then use for the iteration here. And then inside we just have another loop to visualize the corresponding order of the polynomials. And if I just execute this, then you'll see this visualization of the polynomials. So right now here's no physical application for this, but it still provides an overview and visualization of what those functions look like. What's also useful are statistical functions that are built in. I think a very common case is the error function. That is actually defined here by the Gaussian integral or integral of the Gaussian function here without the normalization. But then, of course, you can renormalize it to get the Gaussian probability distribution. And this is just shown here. In general, there is also the Scipy stats module, and this provides a few nicer methods on handling statistical methods, but this we're going to check out later. So the error function is just short or abbreviated as ERF. And it's again just a part of the special namespace. And then we can just use it, for example, to visualize and compare those two. So here's the normal error function, and here's the normalized version. Here's the normal error function, and in orange is then the normalized version for the Gaussian case. Let's come to a bit more physical application of those. So one special kind of function are Bessel functions. And those appear typically in the solution of Bessel's differential equation. And this typically appears in problems like, for example, solution of a circular membrane, like the eigenmode of a circular membrane. And this is actually what we're gonna try to visualize now. So again, we just import the special namespace. And then the Bessel functions are very short in Scipy. I think actually it's probably for historical reasons, like many of those have very cryptic abbreviations. So the Bessel functions here are just JN. Again, I mean, if you don't know what it is, you can always use a question mark in the notebook just as a reminder, and then you will get actually like a more explicit documentation of what it is. And there it says, okay, it's a Bessel function of the first kind with real order and complex origins. So first we can just visualize the shape of those just by plotting it for multiple orders. This is what it looks like. So for order 0, 1, 2, 2, and 3. And then we can actually take a look at a real application of those, namely the eigenmodes of a flat circular membrane. If you want to know a little bit more about this problem, then you can just check out the Wikipedia link here, where you get a more detailed explanation. But basically, just from this Wikipedia page, we can copy the solution of the differential equation describing the problem, and can just code it up in Python. And this is done here. So it's this is in this little method called the Drumhead hide. It takes the parameters n and k, which are the radial eigenmodes, and then the spherical or circular eigenmodes. And then it also takes a radius, which is from the center of this membrane. You're going to see a visualization of this later. I think then it's easier to understand. And then the angle and this additional t factor here. Now we can just set up a range of radii and a range of angles. So the radii just cover the range from 0 to the outer radius of this drumhead, and the angle just covers the range from 0 to 2 pi. And then we can actually create a two-dimensional mesh grid using NumPy. So this basically creates all combinations that we are looking at and we are interested in. Then just for the visualization, we also need this in Cartesian coordinates, so we can just multiply radius times the cosine of theta and the sine of theta. So this is just so far for the preparation. Now let's actually visualize this. Here I'm doing just an additional loop over the different eigenmodes for n and k, so for the radial ones and the angular ones. And then I can rely on a special matplotlib. Or let's start here. So what we can do here is we can add a subplot. This you've seen before, and we're using a special kind of projection here, which is the 3D one. So in matplotlib, it allows also to plot three-dimensional data. Then we're evaluating the drumhead height function for the given theta and radius and the given n and k, and then we get back the amplitude of the membrane at every given position that we specified with radius and theta. And then we plot this as a surface plot in Matplotlib code using this plot surface method. And the rest is just setting title and removing the axis. So this we can now execute. This might take a second on your machine as well, but then you can see actually the visualization here. So this is the 0 eigenmode of the membrane. Then here's the second radial eigenmode, the third radial eigenmode. And then we are looking here at the different eigenmodes from the circular part. So this is just a nice way then of visualizing and, for example, having like a real world example. And there's actually another application to this, or like a nice application. This I'm not showing interactively, but in the scripts folder, you can actually find a script related to the drumhead here, and this creates an animation of the same thing. So calling again the drumhead height function for multiple times, and then seeing like what the amplitude, or how the amplitude of the membrane changes with time. Here I'm just showing the result, but you can actually take a look at the scripts folder to see how this is achieved within matplotlib. And now if I run this, you can actually see how the membrane resonates. And I think this is just the 1-1 eigen mode. Okay, now let's come to the next topic, which is ordinary differential equations. So there are very, or a lot of problems, of course, that can be described in physics with ordinary differential equations. And Scipy provides you some functionality to solve those. This is a nice example, I think, that came up with that Philip Munz came up with, but actually it's so the scenario that we are looking here is a zombie outbreak, but of course it's also like the basic of any kind of pandemic modeling. I don't know, maybe you have taken a look into recent modeling of COVID, or then the basic of this is always the same. So here the scenario is that there is a zombie outbreak or a zombie apocalypse, and of course humanity is inevitably doomed. But this can be modeled in a simple manner. So typically we are describing this here with 3 differential equations. So the first one shows the variation of the total number of susceptible humans. So this is parameterized by, or is described by S, and this is the change with time. Then there's the number of zombies, and there's then the number here of the removed persons that have died either from natural causes or possibly a zombie attack. And those change and depend, of course, on the other quantities. So there are a few other parameters in the model. So the first one is the parameter called beta. And this describes when susceptible becomes a zombie through an encounter with a zombie. So if you encounter a zombie, then you're gonna change into one. Then there are natural causes of death by humans, which are parameterized by this delta fraction here. And then, of course, humans can also be removed in the class and can resurrect and become zombies again. So if people have died from natural causes, then they can still resurrect and become a zombie. And this is parameterized by this gamma parameter here. The question now is, so we can also take a look at the reference here, just for the details. The question now is, can humanity survive the zombie apocalypse? And this we're trying to answer now. There's one method in Scipy that helps you with this, and this is called solve IVP, and this basically does the entire job for us. So if you go to the Scipy documentation about this function, so here we're just citing, then you can just say, so this function numerically integrates a system of ordinary differential equations given some initial value and boundary conditions here. And in our case, T is this one-dimensional independent variable, which is the time. So we want to see how evolves the number of zombies and the number of humans with time. And this is just an n-dimensional vector valued, and yt is this n-dimensional vector valued function, which then determines the differential equations. We're going to see how to define this then in code below. And the goal is now to find yt approximately, so that it satisfies the differential equations, given some initial state that we're starting with. Okay, so now we have to translate this formula into code. This is done here. So first, we just define our parameters here. So here we just choose a certain set that we can work with. So we have B, which is the birth rate. Then we have delta, which is the rate of natural causes of death. This is just set to 10 to the minus 4 here. Then we have the transmission coefficient here, which is basically which parameterizes like what's the rate or what's the probability of a human to become a zombie after encountering it, or like the rate of encountering. You cannot differentiate those, but the same, it parameterizes the same problem. Then there's also the resurrection rate. So people that have died can become or can resurrect and then become zombies. And then there's a rate of destroyed zombies. So of course, like the humans will not give up, but they will also fight against the zombies. And this is parameterized by this vector alpha. Then we choose the initial conditions. So we assume a population of 5,000 people right now. And then at the beginning of the zombie outbreak, there are 0 zombies. There are 0 dead people. And this we just summarize into this initial condition vector. So this is just the API that Scipy uses. Then we give everything or define everything into this F model function that is to bring it in the form that is required by Scipy, which is done here. So we have this method F, which takes the time parameter and the y or the state parameter, and then it returns the corresponding differentials, and this is easily defined as here. So we take the parameter vector, and then we have this after a certain time step. Then we have a certain number of people here, certain number of zombies, and certain number of dead people. And then we can just put this into the equations that we've defined above and defined in the model by Wundt et al. And then we just return the differentials here again as a vector. And now we've brought it into the form that Scipy can actually solve it. Once it is exactly in this form, then we can just choose the start and end value of the t parameter and the time. So here we're assuming 150 days of zombie apocalypse. And then we can put everything into the solve IVP method. So we put in the method here, we put in the start and end time, we put in the initial parameters that we've defined above. And in addition, we just give a grid in which the time should be evaluated. So here we're defining the time step that is used for the solution. Okay, let's run this. Oops, I forgot to execute the cell below, cell above. So this runs rather fast, but now we can actually take a look at the solution. This is what it looks like. So if you take, or this already visualizes it. So let me just show you. So the type of the solution here is an ODE result, and this bundles the complete solution of the problem into a result object. And this is very handy, and you can always take a look like what are the properties of this. So in addition to the actual results, Scipy also returns then, for example, a message saying the solver successfully reached the end of the integration interval. It also tells you like what is the number of function evaluations, and this time we've predefined it to 200. Then there's just a flag, for example, saying whether it was successful. So this can be useful in certain cases because the problem might not converge, for example, and then you don't get a success. What we're actually interested in then is the solution of the problem. And this is returned in the y vector here, and this is now just the evolution of the different rates and the different things we're interested in. So we have the initial population, we have the zombie population, and the population of dead people. And this is contained in the first axis of the NumPy array, and then the time evolution is stored then in the second axis of the NumPy array. And now to visualize this, So to visualize the number of survivors, we can just access the first dimension here in the NumPy array and get all the entries in the second one, and then the same here for the zombies, and then we can actually visualize this. And then you can see that at the beginning we basically have 5,000 people, and then the zombies start to attack, and then there's an even point, and then the zombies take over, and basically humanity is doomed in this scenario, and all people die, and there's and zombies take over the world. There's actually a way to play around with this a little bit. So the exercise here would be to save the world. So the starting conditions and the parameters here are like a very, very pessimistic model. And there's basically just one, or it's a very, very pessimistic model, but you can start, for example, to play around a little bit with the parameters of the model and then see how it evolves. So for example, you could just say, let's increase, for example, I don't know, let's decrease a little bit the transmission coefficient. Then we would expect, for example, by a factor of 2. Then we would expect in this case, okay, this result is actually a little bit unexpected to me. So it just happens faster in this case. But I just encourage you just to play around a little bit with the parameters and see like what's the state that you end up with. There is one way then, for example, to save the humanity, and this is that one could introduce a cure or a vaccination to the problem, so you can make yourself immune to become a zombie, and this can be introduced as an additional parameter in the model. For example, as a new constant row here, which models the effectiveness of the cure, and then the ODE here can be extended by this term, and then there's a way that you can actually save the humanity. This is sketched in the solution here, but you might want to try it yourself first, and then just take a look a bit at the solution. There's another much more complex example. I think Max already has shared this nice animation of a double pendulum, which was included in this lecture. Again, this is just contained in the scripts folder because it runs rather long. But this is basically the result. So there's a more complex set of differential equations describing this double pendulum. But then in the scripts folder, you can actually take a look at this example that creates this animation here. And you might also just want to play around with this a little bit. Okay, another big and important topic for Scipy is numerical integration. So this again is a very common thing that you might encounter. So you want to numerically integrate a certain kind of function. So you're basically just solving the problem here. And there are a few standard methods implemented in Scipy for this. So one standard method is just numerical quadrature. and Scipy provides a series of functions to solve this, for example, quad or double quad or triple quad so this is for a one-dimensional integral, two-dimensional or three-dimensional one, etc. And those are defined in the integrate namespace. So you can say from scipy.integrate, import quad, double quad or triple quad. And then the quad function takes a large number of arguments that can actually be used to fine-tune the behavior. Again, just as a reminder, you can always use the question mark to see how those are defined. So it takes a function that you might want to integrate, then it takes the boundaries for the integration A and B, and then there are a few numerical parameters where actually I don't even understand all of them, but you can specify, for example, the precision of the integration as an absolute error or as a relative error. You can also specify weights for the integration. And again, just use the question mark just to check what are the options available. Alternatively, you can also just type the parentheses here just as a reminder, and then if you hit Shift-Tab, then it will actually show you the signature of the method here, and then you can interactively take a look what are the options. Okay, let's just use it in a very, very simple way. So let's just integrate a parabola. This we can just define as a normal Python function. So we just define f of x, which returns x squared, and then we integrate this from 0 to 1. And the way to call it is just call using the quad method. Then we pass in the function, we pass in the lower range and the upper range for the integration. And then we print the result and actually visualize it, just to make it to understand it a little bit better. The solution of the integral, as expected, is 1 over 3. I think you can easily convince yourself that this is the correct solution. I think you can see that also the default precision is actually rather high. So the absolute error that you get for this case is 10 to the minus 15, which is probably over precise for many scenarios. Let's just take another case. For example, this is just a super simple function here. It does not have any additional parameters, but there might be other cases that have additional parameters. So we could get back to the case of this Bessel function that is defined in NumPy special by Jn, and this has this additional n parameter. And the way to specify this in the quad method is this with this additional args argument. And those additional args are then passed on to the method after the first argument. So just to verify, so you could just say like, oops. Yeah, okay, so we've done this, returned the result already. So the arguments here are just the ones defined after the x here that are additional. So if this would take another argument, like, I don't know, I think for the Bessel function here, there's no other argument, but just to verify, for example, here we could pass on 5, and then the 5 would be defined by the k, and the 3 would define the value of the n here. Might be useful just to keep in mind. Okay, then what can be handy in some cases, I mean, here we've defined a super simple function using the def syntax of Python. In some cases, one can also just use a lambda function to write it a little bit shorter. This is a so-called nameless function in Python, instead of just explicitly defining the function here using the def syntax. Here's just the example of the Gaussian integral, or exponential to the power of minus x squared. And this we integrate from minus infinity to plus infinity. And then we can even, in this case, compare it to the analytical solution. So the result in this case is well defined. So it's the square root of pi. And this is the analytical solution. And here you can see the numerical solution. And again, like, the precision is very high. Let's take a look at a higher dimensional problem. So here we're defining a method, a function in 2 coordinates. So it varies with x and y at the same time. So it's basically a Gaussian or a Gaussian shape in two dimensions, and we can also visualize it. For the visualization of this, we just, again, compute the mesh grid here, given the x and y space. And then we just evaluate the method on the given coordinate grids, and then we can use this plot surface here to visualize it. Maybe let's just execute this part first. So this is what the function looks like that we want to integrate. And now we can actually integrate it. And what we specify for the integration here is, so of course, as the first argument, we just give the integrand. As it's a two-dimensional method, we use double quad instead of the single quad method. And then we have to specify the boundaries. And in the two-dimensional case, this is a bit more tricky. So you can specify first the boundaries of the independent variable, and then you can specify the boundaries of the dependent variable just as a method. So here it takes the x as a first argument, and then it just returns the boundary, possibly depending on the independent variable. In this case, it does not depend, and we can just return a constant value. So in this case, -2 and 2. And then if we execute this and actually do the integration, then you can see here the result is 1.1. I think if we increase here a little bit the range, then this should actually converge to pi. You'll probably find also just like a few more in-depth examples in the Scipy documentation, but I think that's like the basic usage of this. Okay, we could take a look at another method. Let me just check what we're almost halfway through. I think this roughly fits, so we can actually take a quick look at the exercise here. So for the exercise, you could actually compare the integrals to some of them, or you could compare the integral for a special function. So here's this example use case of the circumference of an ellipse. And the formula to calculate it is given here. And as far as I know, oops, yeah, this is just given here. And this you can now solve numerically. And then there's also an appropriate function actually in the Scipy special package that allows you also then to compare it against the implementation that you have done as a result. Again, you could just load the solution here and then verify against the sample solution on what you've worked on. In this case, also the ellipticity is just given by this expression here. Okay, I realized that I'm going a little bit fast here. As I said, I mean, with the exercises, there's unfortunately not enough time, I mean, to go really through it in detail. I might come back to it, but please make use of the Slack channel just to ask questions. So try it yourself, and then ask questions if you encounter any problems. Then we'll be around just to answer those. What I can provide here right now is just to give you the overview on the functionality, so that at some point in time, I mean, you might encounter a certain problem in Scipy, or a certain problem in your daily work, and that you remember, oh, there was something in Scipy actually to solve the problem. As a general comment, I mean, this is probably just the way that you still typically work with Python, right? I mean, if you encounter a certain problem that you want to solve, then you typically just Google for whether there's already a solution or already a package that provides a solution for the problem that you want to solve. And for many of these basic stuff, the answer might be Scipy. Okay, let's continue with a little bit of signal processing. So Scipy also provides some functionality to do basic kinds of signal processing. So a very, very common operation is convolution of two continuous functions. Here you can just recall yourself the definition of the convolution. And typically this happens in the real life. For example, if you take data and the data is mirrored by the detector of any kind, for example, to model the point spread function of an instrument, then you can apply it with the convolution, or very similar, for example, for the energy resolution or scenarios and applications like this. The import of the sub package is just from Scipy import signal. And just for a visualization and demonstration, we create these two rectangular signals that we can visualize. Then we can pass on. So we're defining this vector f and g, and then we convolve those. And the mode here is same. This means the output shape is the same as the input one. There are different there are different modes. Again, just use the question mark operator to check. Let me just execute the import here. SciPy convolve. So it takes the first array as an input, the second one, and then there are different modes. There's full, valid, and the same. And here you can see how it is defined. There's another method keyword that I'm gonna explain in a second. Okay, let's just visualize the result that we've computed here, just using matplotlib. So this was the first signal that we've defined as this rectangular signal. Then we have the filter impulse response, which is defined as a smaller rectangular signal, and the result then is the filtered signal, and you can see that you just get this ramp here as expected. The naive implementation of a convolution is typically very, very inefficient. So it takes order of n squared steps to get the result, where n is the size of your vector. And typically, and also I think in practice, one often uses an FFT-based algorithm, which is much faster. So just as a quick reminder, you can also describe a convolution as a multiplication in Fourier space. So if you take the Fourier transform of the first function and then multiply it with the Fourier transform of the second one, and then if you do the back transformation, then you actually get the convolution of both input signals. The question is now, so typically this FFT-based convolutions are faster, and what SciPy provides for you is actually some kind of heuristic to automatically find like what is the fastest convolution method for your problem. And this is specified in this convolve. This is specified with this method keyword that you can find here. So what you can do is you can either choose you can choose between the direct convolution or the FFT convolution, or this auto mode, which is the default one, which chooses just the convolution operation, which is faster. I think this comes in very, very handy, especially if you're doing the convolution of, I don't know, large arrays or two-dimensional arrays or three-dimensional arrays. What I found in my daily work is that the FFT convolution basically always wins. Even in the case of very, very small vectors and small arrays, it's still in many cases faster. But it's a good practice just to rely on this generic API here with the convolve, which chooses the method independent. Chooses the method just given the built-in heuristic, and then chooses just the fastest method. What's also contained in the SciPy signal namespace are certain window functions that might be useful to apply it with filtering operations, and those are also available in the same namespace. So, for example, there's a Nuttall window, Hannings or cosine, triangle window, Blackman-Harris or Blackman window. Just for visualization, we can just plot those. You might want to choose the one which is suitable for your problem. I think this is interesting in certain applications. What is also implemented in SciPy is the correlation or cross correlation. Basically, it's the same. It's basically the same operation as a convolution, except for the sign in this term here. But this can be used, for example, to find or to cross match two different signals. And this is just the application that I want to show here. So we're defining two signals here as a Gaussian pulse. This is evaluated in a certain time range that we define between -1 and 1, and then using 600 bins. And then the second signal we just define with a certain offset to the first one, so it's offset by 0.25 in this case. And then we can compute the cross correlation between two signals, and then we are looking for the maximum. So we shift both signal, or we shift one signal over the other, and then we look like where's the place with the strongest correlation of both signals. And this is done with this argmax method of NumPy. Let me just execute this. So we can at least verify that we found the right offset here. Of course, it's only as precise as your sampling size here, but you can see that it's reasonably close to the offset one. So this is very, very handy if you want to cross correlate two signals and, for example, find an offset. Let me just provide a bit more better visualization of the problem. So here you can just still see the reference signal. Then you can see here the offset signal. And here they can find the cross correlation, and there you again find then the maximum at the given offset. So I think this is like a very, very nice application of this. Another very interesting application is given as the exercise here. So for the application of this signal filtering, so there we can imagine a scenario where an alien civilization wants to communicate with us, and it uses just binary encoded signal that we can, for example, record with large radio telescopes. And now if you assume that the aliens are just using binary signals, and we have a given clock speed and a certain sample length, then we can actually decode or try to decode the signal. Just as an illustration, so in this exercise, the example signal is provided in the data folder, but just as a general or just as a hint for the exercise here. So this is what a signal would look like. So here's a 0, here's a 1 when the signal goes up, and then if it goes down, it's 0, 0 again. And then the actual signal then that we're looking at. And this is roughly what this looks like. So here you can see there's a lot of noise, but then there might be a chance to find a signal here if we actually put this into chunks, or put this into chunks of a given sample length. Again, the example solution here is provided, and if you do it correctly, then you should end up with a nice message sent by aliens. Okay, let me come to another application. So we have already talked about the Fourier transform in the context of the convolution, but there might be other cases where you're just interested in the Fourier transform, for example, to visualize the spectrum of a certain signal. And for this, Scipy provides another subpackage, which is called FFT-Pack. And this is just a wrapper and that to this classic FFT-Pack implementation, which is like a very efficient and well-tested FFT library written in Fortran. I think now there's actually another one around, which is called PocketFFT. I'm not sure this is definitely available in NumPy. I think I'm not sure whether it's available in Scipy, possibly not. But we can still rely on this FFT-Pack one. Let me just show an example. So it's imported from Scipy as FFT-Pack, and then we just create an artificial signal. So we choose the number of samples, we choose the length, and here we have the sample size. Just defined by the length divided by the number of samples. Then we create the space that we want to use for the sampling. So we use NumPy lint space to create this area of x values here between 0 and the length and given the number of samples. And then we create this artificial signal just given as a harmonic. So we just rely on NumPy sign, and then we have multiple frequencies that we're using here, so 8, 3, and 32, and those are weighted by different amplitudes. And then finally, we just add a little bit of noise using the random generation or using a normal distribution for this additional noise. And then we can actually plot this. So this is what the signal looks like. Might look random at first place, but now we can use the functionality in FFTPack to actually compute the fast Fourier transform of the signal and transform it to frequency space. There's a little helper method that does the same actually for the for the frequency values, and then we can use this to visualize the spectrum of the signal. And there you can see there are, as expected, like 3 clear peaks that we've defined here in this artificial signal here. Okay, let's move on to the to GammaPi. Sorry, to Scipy statistics. The GammaPi session will be Monday next week. But GammaPi also feeds us a stats module. That's why I was confused for a second. So Scipy has the stats submodule, and this contains like a large number of statistical distributions. So often you're dealing with problems. I don't know. You want to estimate false detection ratio, or you have a normal distribution of a certain problem. And those are all documented and listed here in the Scipy stats module. So there you can see that there's like a lot of built-in distributions available. There are many names that one does not even know. There's the beta distribution, Cauchy, chi-squared distribution, d-gamma exponential distribution, basically everything probably you would ever need. But we just for visualization, we're just gonna start with a very simple one, just a normal distribution. And this we just define with a mean and a sigma. And this can be instantiated with the stats.norm. And then if you take a look actually what is returned. Then this is one of these RV stat objects. Now the question is what can you do with this? A good way to find out is, again, just as a reminder, you type a dot, then you hit tab, and then you can see what are the methods actually defined on this object. And there you can see that there's really like a huge number of methods defined here. For example, mean, median, moment. You can access the PDF. You can access the probability density function. You can access the probability mass function. You can access the cumulative distribution function. You can access the entropy. You can access the different moments. Here is just below just another overview of this. I think in practice you will probably only need a subset of those, but still it's handy to have those available. There's also the log PDF, which is often useful for minimization, etc. Okay, let me just show you an example and just visualize the probability density function of this normal distribution and the cumulative density function. So this is done here. So we just set up again the range for the variable and the data space that we want to work with. So we evaluate this between -3.5 and 3.5 sigma with 200 bins, and then we just create these two subplots, and then we can evaluate the PDF and just plot it using matplotlib. The same for the cumulative density function. Let me just do this first. So this is what it looks like this red shape here for the Gaussian distribution, and then for the cumulative one. And then in addition, there's this little method called .rvs. And this lets you actually draw samples from this distribution. This is, of course, very handy if you want to do simulations. So if you want to draw samples from the normal distribution, for example, 100 samples, then you can just use this RVS. In general, of course, I mean, you could do the same and achieve the same in this case just with NumPy random. The advantage here of Scipy is, of course, that it provides just much more or like a much bigger selection, as we've seen before, of available distributions. In the simple case of this normal distribution, you could basically just stick with Scipy in this case. But the nice thing again then about Scipy is, of course, that the API of the different distributions is always the same. So all of these distributions will have this RVS method, will have the CDF, will have the PDF method. And also, for example, for visualization, this is also very, very handy. I mean, for the sampling, you could rely on NumPy as well, but in this case, you want to visualize it, and then you can just work with the PDF and CDF. Okay, so this was just this simple model. There's another very common set of distributions you might want to work with. These are discrete distributions. Again, they offer a very, very similar API, so you can draw from the discrete distribution. You have the probability mass function, the log of the PMF. You have the survival function, this I haven't mentioned before, which is defined by 1 minus CDF. This is also very handy in given situations. You can compute the mean and median. I think probably the most, or one of the most common discrete distributions is actually Poissonian distribution. This you can then instantiate with stats.Poisson. And then you provide the mean of the distribution as a 3.5. And then we can actually do, again, the same plot as we've done before, but just for the Poissonian distribution. So here you can see the probability visualization of the probability mass function. Then the same here for the cumulative distribution function. And then again, we've used this .rvs method to draw samples from these distributions, like 200. And then we histogram this just to verify that the same shape is the same as, or approaches the one that we expect. Of course, you can draw, I don't know, 10,000 samples here. And then you get like a much better approximation. Just to conclude here, so the mean and standard deviation and variation are all accessible. So the first one here was the normal distribution. So the mean we've defined as 0, standard deviation as 1, and then the variation is also 1. And then for the Poissonian case, as you can see here, you can only define the mean, but it's correlated with the standard deviation as a square root of the mean. And then again, the variation is just 3.5. So this is what is expected. And again, those just Scipy features like a lot of those, and you might want to check like which one you want to use. Okay, let me come to the next class of algorithms and problems that you might encounter in your daily work, and this is optimization. This is very common, of course, for likelihood fitting. So if you adapt a certain model to your data, but it can be also, I don't know, could be also different problems. The first one would be just like classical minimization. So you want to find the minimum of a simple function with only a single variable. This function here we're just defining like so. It's basically just a given polynomial here. Of this kind, it's basically arbitrary, but this is what it looks like. So it basically defines a global minimum and a local minimum here. And this we can now try to find both of those using Scipy. And Scipy has this single API for the minimization of scalar values, which is called minimize scalar. And this we can use, and then you can actually choose from multiple methods for the minimization, which are then chosen under the hood. The way to use it first is basically very, very simple. So you can just pass in the method, and that's it. And then you can let it run. But in this case, as you can see, and for the visualization, it's not necessarily guaranteed that you get the global best minimum, but it just finds some minimum, which could be arbitrary. To avoid this kind of behavior, you can give, for example, an additional bracket for the value that you want to, or where you require the value to be in. So we strict it here now to the negative part, and we can just give it as a bracket here from -6 to -2, and then in this case, oops, the plotting is gone now. Let me just check whether the result is actually correct. Sorry, no, I just missed the plotting of the actual method here. And now you can see that it actually found the global minimum. So you have the possibility to specify certain brackets for this. Again, just take a look at the docstring. So minimize scalar. So it takes brackets, it takes bounds, it takes certain arguments. So just in the case, or in the same case as for the integration, if you have additional arguments to the method that you have defined for the minimization here, then you can just pass those as args. And then there's the choice between multiple minimization methods. The default one here is the brand method, which I think is a very robust one. But then there are multiple other methods that you could rely on, for example, bounded, golden, etc. So in some cases, you possibly find convergence problems, and then you could choose a different method to solve your problem. Very similar to the ODE case, actually the result is bundled in a certain or special kind of object, which is called this optimized result object. And this has additional information. For example, you can check the number of function evaluations needed to find the minimum. Or you can check whether it actually was successful according to a given heuristic used by Scipy. So this might be useful additional information that you want to rely on. Then another use case is, of course, like minimization in more dimensions. There's this classical example of this Rosenbrock functions, which is often used to test minimization algorithms. This is actually defined like so. Just to visualize it a little bit, this is what it looks like. And there's actually a minimum in the center, but as you can imagine somehow from the shape, the convergence is not simple in all cases. But anyway, for this we can now rely not on this minimize scalar, but on a method called just optimize.minimize. And there we just give the method as this lambda function that we've defined with this as this Rosenbrock 2D method, and then we can pass on the additional starting values that we want to use for the minimization. Here we just start from 5, from the point 5 and 2. Then we can actually run the minimization here, and then just visualize it and check the result. And in this case, so here's the minimum that it found, and by definition here it was set to 1, 1, and this was successful. Again, this also the 2D minimization returns a result object that you can check. In this case, it's a little bit more complex, but it has, for example, this additional method. So it says optimization terminated successfully. And this is useful also for debugging. There might be situations where this just does not converge, and then you might find out why. Status here is 0. So this can become useful. It also has additional information such as the Jacobian matrix or the inverse Hessian matrix, which is then already an estimate for the or that you can then use as an estimate actually for the covariance and the error of your of the result. Okay. Another very common minimization problem is just least square minimization. So there are 20 minutes left. I think this we can still go through. So let's presume that there's just like a linear weighted combination of variables defined like so. Then this can be actually reformulated as a matrix inversion. And this is just shown here. I mean, right now, I think you don't have to understand the details here. This is just the reminder. I think the situation is just very common. So you have, for example, a given set of, I'm not gonna explain in detail, but you have a given set of data, and you have, for example, some parameterization or some parameterized model that you want to fit to the data. And this you can do, for example, with least square optimization. And the challenge here is just to bring it in the right form so that Scipy understands it, and this is this is described here here above. Let's take a look at this example here. So here we want to fit a given polynomial to the data. This we define with x as the independent variable, and then we have these additional parameters defined by beta 0, 1, and 2. And these are just the prefactors then of the given terms here. Just as a demonstration, then we just evaluate this little toy model that we have here, and then we just to simulate a measurement process, we're just adding some noise to this, and then we can actually visualize this. Now you can reformulate this problem as the matrix that Scipy needs, and this is just, as you can see here, just given by the given polynomials of the x. So you have x to the power of 3, x minus 4 to the power of 2. So this corresponds to this one here, and x to the power of 4. And then you can actually solve for the coefficients. And this we pass in now to this optimized linearly square solver. So here's the coefficient matrix. Then we have the actual data that we want to fit to. And then we can actually visualize the result like so. So here we're plotting the truth that we've used for this toy simulation, which is shown in gray. Then we're using then we're visualizing the red one, which is the result of the minimization, and then the blue are just the data points. If you have a slightly or if you need, let's say, like a more handy or smaller API for this, then Scipy provides this curve fit method. This is shown here below. Here again, we just define a certain model that we use for the simulation. Then we just evaluate it at some noise, and then we can actually execute the curve fit here. So we pass in the same method and then solve for the different parameters that we've introduced here. So in this case, it's scale and the location, and then we can also visualize this. This curve fit returns the best fit parameters, so the best fit scale and the best fit location. And in addition, it also returns the errors for those given as the covariance matrix. Just as a reminder, the covariance matrix contains then this two-dimensional array here for both of the parameters, so for the scale and the location. And then if you access the diagonal elements of those, and you take the square root, then this actually gives an estimate for the error of the best fit parameters that you have. Okay, there's another little exercise on curve fitting. So there's a sample data that we provide, like the average temperatures for Munich. And there, the question is just to fit a certain model to this average temperatures. to see, for example, whether there's a certain variability in the data, or, for example, a certain period. Those temperatures change with. Okay, one last class of minimization problems, or related to those, is root finding. So there might be the case that you want to find the root of a given function. This is often very similar. So, for example, for one-dimensional problems, so instead of finding the minimization, finding the minimum, you could take the derivative of the function and find the roots. For this, also Scipy provides a uniform API in the optimize subpackage which is called root. Here we have this example. Again, this example function that we want to find the roots of. And as it's still the same function as above, and as it has, except that it's slightly shifted so that it crosses the 0 line. And then, as you can imagine, it has multiple roots. And for this, we can specify again the brackets to find those roots. So if I run this code, then you can actually see that it found all the 4 roots that were specified, like close, or were specified by this initial estimate here. Again, it's like what I would call like a single entry API. So we have optimize.root, and then if you check what are the options available, then you can see that it takes a function, it takes the initial estimate for the root, it takes additional arguments, again, very similar to the integration and the minimization. And then it also takes this method keyword, which allows it to choose between different methods. There's a hybrid solver, there's linear mixing, whatever. In addition, which this might be useful in some cases, you can also pass in the Jacobian if you have it available. And then you might get like a more stable conversions for the problem. Or you can specify a tolerance, like what's the precision required for the roots. Okay. I think the second last topic here would be interpolation. I think this is also like a very common problem that you encounter in your daily work. Let's just define a little example method, just a sign. And then we want to, or then we sample this example method at a given set of points here defined by the n. And those sampled points, then we want to interpolate in between again. So this is done here. So here we have the measured points sampled at these given n's here, and then we interpolate the measured points at a fixed grid, and this we're doing here. So for the interpolation, then we're specifying just a much more dense data space. So these are the measurement points, and these are the ones that we are used for the interpolation in between. Just to explain here, so the thing that we are relying here is Scipy interpolate interp 1D. And this is just called with the data points here given as y measured and the locations where those are defined. And then this returns, so if you check the type, this returns this interp 1D object. And this then basically behaves like a continuous function that you can interpolate at any given position. So if you check the doc string here, then you get a little bit more information. So one additional parameter here is the kind. So what kind of interpolation do you want to choose? So the default one is linear, but you can also choose, for example, the nearest neighbor interpolation, or you could use quadratic or cubic interpolations. In addition, what could be useful is this axis keyword here. So actually the data that you put in here, this could be higher dimensional, so it does not have to be one dimensional, but you can then interpolate along a given axis. And this is, for example, one of the main advantages over a method like numpy.interp. So NumPy also has an interpolation method built in, but this, for example, does not allow to interpolate along a given axis. And also, I think, for example, does not allow for extrapolation. This is something, for example, this interp1d method provides as well. Okay, so here we just creating two of these interp1d objects, one with a linear interpolation and one with a cubic one. And then we just visualize how this looks like. So here's the black dots are the noisy data points. Then we have the true function as a reference. And then in blue is shown the linear interpolation, and the result looks expected. So there's linear interpolation between these given data points. And then one could use the cubic interpolation, for example, to better approximate the initial function. So you can put in some prior knowledge, for example, to improve your interpolation. I'm not showing this here, but just in general, of course, in Scipy, there are also methods available for higher dimensional interpolation, so interpolation of 2D or 3D data. Just as a side comment, what I found often useful is this this regular grid interpolator class, just for you to keep in mind. So if you have interpolation of higher dimensional data, then this might be one thing that you want to look at. In addition, there are further interpolation algorithms based on splines. And you might want to choose the one which is suitable for your problem. And this might depend also just on, I don't know, for things like what's the best performance, etc. for the certain kind. So often you have to wait between getting a good performance and getting a good precision. And this regular grid interpolator, I think, has a very good performance, but typically only provides linear interpolation. Just as a side comment. Okay, then there's one last module here that we could take a look at in Scipy. This is Scipy IO. So often you have various kinds of data. I mean, typically, of course, like all the data is just like some kind of n-dimensional array. But there are certain file formats to store those with additional metadata. One example that we're taking a look here is audio data. I'm not really sure if some people here work with audio data during their daily work. I remember I've used this in the past, I don't know, just for fun, because you can play around with it a little bit and can actually make NumPy arrays audible in a given sense. So here's just one example where we can use this. So we just define an audio signal. In this case, it's just the Lyman, Balmer, and Balmer series of the hydrogen atom. So this defines the frequencies, and then we just choose the given harmonics defined by M, and then we can create the sound signal here. So we just use a sine function. Given then the frequency provided by the Balmer or Lyman series, and then we evaluate it in time. This we do for a certain time interval provided by lint space. The duration here would be 10 seconds. And the rate that we're using, this is just a convention used for this wave file, would be 44.11 kilohertz. And then we can create this signal by evaluating the sound function here, given the certain harmonics of the Lyman and Balmer here, and then we just sum up everything, so a linear combination. And then we can visualize it, and then we can also, using this wave file method here, to actually write it to disk in the standard wave format. So this is what the signal on a small part of the signal looks like. Just to verify that this actually worked, here's a little trick to embed an audio player in the notebook, and then we can reload this audio file again, and then we can actually listen to it. I think this might not work in the live stream, but of course, I mean, you can locally just execute it. Just let me check. I think I accidentally wrote it to the wrong folder here. So here you have to correct to data. I think you can probably not hear this right now, but you can actually execute it locally, and then you should be able to hear it. Then as a last exercise, there is, again, an example wave file, and the exercise here is just to plot the frequency spectrum of this. I think you've seen how to compute a frequency spectrum somewhere before in the notebook, and then you can actually load the data and show the spectrum. Okay, I think that's it. I realized this was a lot of content in a very short amount of time. As I said, I mean, the goal here was not necessarily to make you everything understand in detail, but just to give you an overview of what Scipy provides, the functionality, and then if you encounter some real world problem, then just remind yourself like there might be a solution in Scipy, and they here just have like the minimal working examples that show you how you can work with this. Okay, I think there is some time left for questions.
Yes, I think we can take 5 minutes. Thank you very much, Axel. That was a very nice overview of Scipy, and yes, people can go back to the exercises and work themselves on that.
And please make use of the Slack channel all the time.
So maybe one question, what are the differences between the FFT from NumPy and the one from Scipy, and are there advantages on using the Scipy one?
That's an excellent question. I think the underlying implementation is actually different. As far as I know, I think the recent implementation in NumPy changed to a new small library called PocketFFT, which I think has like an excellent performance. And I think like the one in Scipy with the FFT pack, I think this is rather like a, I don't know, maybe a legacy Fortran module. I think in terms of performance, I've never compared those. I think in this case, just try it out yourself, and I don't know, maybe choose the faster one. I think maybe that's already it. I think this is actually true for a bit of other functionality. So there's some duplication. This is just what came to my mind. I mean, of course, there's also NumPy linear algebra functionality. And there again, part of it is duplicated. I think the default assumption here would be if you have Scipy already installed, then you would just rely on the Scipy functionality. Typically, it offers you more ways, it offers you more functionality in general, and then typically also for the individual methods, it typically offers more parameters or more methods you can call into under the hood. And then, so I think the default would probably be just use Scipy if you already have it. If for some reason you want to avoid the dependency on Scipy, then you just rely on NumPy.
Okay, thanks. I had myself a question. There are also other packages for minimization that exist out there. What are the advantages of these compared to Scipy? Or
yes, this is a very, very broad question. I would say like Scipy offers just the bare functionality of the minimization, but it does not necessarily offer a nice API, for example, to define models or to define or for example, to work interactively with it. I think a very, very common package that is used often is a package called iMinui. And this is a Python wrapper to the Minui implementation, which is used in high energy astrophysics. I'm not sure. Maybe we'll learn a bit more about this in the scikit-help tutorial. But the advantage here is just it offers a much nicer API for interactive work, and you can directly get For example, I've shown how you can get the errors from the covariance matrix, and this would be built in this API already, so you don't have to take the diagonal and the square root, and then it offers nice interactive visualization of the results rendered as HTML and things like that. So I think this is the main advantage. Then, of course, I mean, you can enter also the field of machine learning and minimization things like TensorFlow and Keras and whatever. And I think at this point it just gets too broad. I think Scipy offers the typically solutions for, I would say, like small scale problems. So if you do minimization with up to a few 10 parameters, this might be fine. If you have a more complex problem, or if you encounter, for example, I don't know, convergence issues, I don't know, Minui might be more interesting. What I found in my daily work is typically that there is not necessarily a single answer to like what's the best minimization algorithm. The answer is often you have to try a few ones and then just see which one works for you. But Scipy is like a very good start.
I agree. Maybe a last question that I have also. In the example you showed, Scipy seems pretty fast to solve equations and everything. Is it built on top of compiled libraries or?
Yes, I mean, Scipy basically just provides a Python API to compiled libraries, which are then used in the back. I don't know all the details, but I think Scipy includes some Python code. It includes C code. It includes even some Fortran code that is used under the hood. So it's basically, I think, often it just calls into legacy libraries that have been around for forever, and just builds and provides a nice Python API to make the functionality then accessible for NumPy and Scipy users. In general, Scipy, I think, has good performance. I mean, in some cases you might have to. I mean, the problem is rather, I think, within Scipy to choose between different methods. One example was the convolution method. There, actually, Scipy provides a solution, so it will actually choose the faster one for you. But this is not true in all cases. For example, for interpolation, it's not true. And there you have to play around a little bit and just check the different options that you have. I think over time, Scipy has actually managed to adapt the API to make it more uniform. So, for example, the different interpolation classes actually have the same API, and then it makes it much more easy to interchange those and see like how they behave in the exact problem that you're looking at.
Okay, thank you. I think it's time. We have now a short break, and we come back at 11 for the AstroPy lecture. So thank you very much, and see you in a while.
Thanks a lot. See you at 11.